Welcome to this session on Fourier transforms. An integral transform of a given function f of t is defined as f of s is equal to integral from a to b k of s comma t into f of t dt, where k of s comma t is called the kernel of the integral transform. By choosing different kernels, we can write different transforms. For example, if we choose kst as, that is the kernel as e raised to minus st, and by choosing the limits of integration 0 to infinity, that is we take a equal to 0 and b equal to infinity, the kernel of the transformation as e raised to minus st, then we get this transformation as f of s is equal to integral from 0 to infinity, here kst is e raised to minus st into f of t dt. This is known as the Laplace transform of the function f of t. We already discussed the Laplace transform. Now, if we choose kst, that is the kernel of the transformation, as e raised to minus I omega t, and the limits of integration as minus infinity to infinity, then this integral transform will become f of s is equal to integral from minus infinity to infinity e raised to minus I omega t into f of t dt. This is known as the Fourier transform of the given function f of t. That is, the Fourier transform of a function f of t is defined as integral from minus infinity to infinity e raised to minus I omega t into f of t dt. It is a function of omega, and the notation is script f of t. This is the notation for Fourier transform, and the definition is integral from minus infinity to infinity e raised to minus I omega t into f of t dt, where f of t may be a real valued function or a complex valued function in t. And the inverse Fourier transform, the corresponding inverse Fourier transform of the Fourier transform is defined as f inverse of f of omega, which is equal to f of t. This is the inverse Fourier transform. Now, we have a theorem. If Fourier transform of a function f of t is equal to f of omega, then at a point t where f of t is continuous, we can express the function f of t as f of t is equal to 1 by 2 pi into integral from minus infinity to infinity f of omega into e raised to I omega t d omega. At t, where f of t is discontinuous if there is some points of discontinuities, then value of this right hand side integral will be obtained by taking the average of the left hand limit and right hand limit of the corresponding point of discontinuity. This is known as the Fourier complex exponential integral representation of f of t. Now, we have to consider the Fourier transform of even and odd functions. We have the Fourier transform of f of t is equal to integral from minus infinity to infinity e raised to minus I omega t into f of t dt. This is equal to integral from minus infinity to infinity f of t into, here e raised to minus I omega t can be written as cos omega t minus I into sin omega t dt, because e raised to I theta is cos theta plus I sin theta, and e raised to minus I theta is cos theta minus I sin theta. Here instead of theta it is omega t. Now, we split into two integrals. This is equal to integral from minus infinity to infinity f of t into cos omega t dt. Here minus I is a constant, therefore that can be taken outside of the integral. Minus I into integral from minus infinity to infinity f of t into sin omega t dt. Now, this is the Fourier transform of f of t, which is denoted by f of omega, which is a function of omega. Now, consider the case f of t is even. This is case 1. We know that cos omega t is always an even function, because cosine functions are even functions. Therefore, f of t into cos omega t means f of t is even into an even function, even into even. In this integral, here f of t is an even function into sin omega t is always odd function, therefore even into odd. Product of two even functions means, for example, x square is even, x raised to 4 is even, therefore product of this x square into x raised to 4 is x raised to 2 plus 4, that is x raised to 6, which is also even. Product of two even functions is always even, and an even function into odd. Consider this example, x square is even, x cube is odd, therefore x square into x cube means x raised to 2 plus 3, that is x raised to 5. X raised to 5 is an odd function. This function, even function into odd, means this will become an odd function. Therefore, by the property of definite integral, this integral can be written as Fourier transform of f of t is equal to, here we can write 2 times integral from 0 to infinity f of t into cos omega t dt. In this case, here the integrand is odd and the limits of integrations are here, upper limit is infinity and negative of the upper limit is the lower limit minus infinity. Therefore, value of this integral will become 0, and the corresponding Fourier transform is 2 times integral from 0 to infinity f of t into cos omega t dt. This is the Fourier transform of an even function. Now consider the case f of t is odd, case 2, f of t is odd. In which case here this function is odd, an odd function into cosine function is always even, therefore an odd function into even function means which will become an odd function. In this integral f of t is odd, sin omega t is odd means an odd function into odd function. For example, x cube is odd, x raised to 5 is odd. This product is product of x cube and x raised to 5 is x raised to 3 plus 5, that is x raised to 8, which is even. Here an odd function into odd function means which will become an even function. Therefore, by the property of definite integral, we can write here, since here the integrand is an odd function and the limits of integrations are minus infinity and plus infinity, value of this integral will become 0, and this will become 2 times value of this integral is 2 times integral from 0 to infinity f of t into sin omega t dt. Here minus I is a constant, therefore minus 2I into integral from 0 to infinity f of t into sin omega t dt. This is the corresponding Fourier transform of f of t. In this case, that is when f of t is an odd function, the Fourier transform is given by minus 2I into integral from 0 to infinity f of t into sin omega t dt. Now, we have to consider some examples for the Fourier transforms. First one is obtain the Fourier transform of the function f of t is equal to 1 for 0 less than or equal to t less than or equal to 1 and f of t equal to 0 otherwise. In all other cases, the function is defined as 0. Hence, find the complex exponential Fourier integral representation of f of t. First of all, we have to find the Fourier transform and also find the complex exponential Fourier integral representation. By the definition of Fourier transform of f of t is equal to integral from minus infinity to infinity f of t into e raised to minus I omega t d omega. This is the here dt. Here the function is given by f of t equal to 1 for 0 less than or equal to t less than or equal to 1 and equal to 0 for all other cases. All other cases means t may be greater than 1 or t may be less than 0. Therefore, we have to split this integral into 2. This is equal to integral from minus infinity to 0 f of t into e raised to minus I omega t dt plus integral from 0 to 1 f of t into e raised to minus I omega t dt plus integral from 1 to infinity f of t into e raised to minus I omega t dt. which is equal to, in this case the function is given by 0, therefore the first term will become 0 plus integral from 0 to 1. The second in the second case the function is defined as 1 into e raised to minus I omega t dt plus, in this case that means t is from 1 to infinity, function is defined as 0, therefore the third integral will become 0. This is equal to 1 integration, we get e raised to minus I omega t divided by, here the integration is with respect to t, coefficient of t is minus I omega, therefore we have to divide e raised to minus I omega t by minus I omega between the limits 0 and 1. That is when t equal to 1 we get e raised to minus I omega minus when t equal to 0, this is e raised to 0 means 1 divided by minus I omega, that is equal to 1 minus e raised to minus I omega divided by I omega. This is the required Fourier transform of the given function. Now we have to write the exponential Fourier, complex exponential Fourier integral representation of f of t, which is given by f of t is equal to 1 by 2 pi into integral from minus infinity to infinity f of omega. Here f of omega means this function, this is a function of omega, into e raised to I omega t d omega. In the Fourier transform, the exponent is minus I omega t. In the complex exponential Fourier integral representation, we have to write the exponent as plus I omega t d omega, that is 1 by 2 pi into integral from minus infinity to infinity. F of omega is 1 minus e raised to minus I omega divided by I omega into e raised to I omega t d omega. This is the required integral representation. That is by writing the Fourier transform of a given function, we can express the given function as an integral. Now the next problem is find the Fourier transform of the function defined by f of t equal to sin t. For 0 less than or equal to x less than or equal to pi, not x, it is t less than or equal to pi, 0 less than or equal to t less than or equal to pi, and 0 elsewhere. By the definition, Fourier transform of f of t is equal to, this is a function of omega and is defined as integral from 0 to infinity, integral from minus infinity to infinity e raised to minus I omega t into f of t dt. That is here we have to split this integral as integral from minus infinity to 0 e raised to minus I omega t into, in this case f of t is defined as 0 dt plus integral from 0 to pi e raised to minus I omega t into, in this interval f of t is defined as sin t dt plus integral from pi to infinity e raised to minus I omega t into f of t is defined as 0 in the interval pi to infinity. The first and last integral will become 0, and the value of middle integral is integral from 0 to pi e raised to minus I omega t into sin t dt. That is equal to value of this integral is e raised to minus I omega t divided by minus I omega square whole square plus 1 square into minus I omega sin t minus cos t between the limits 0 and pi. Which is equal to 1 plus e raised to minus I omega t divided by 1 minus omega square. Here not t, when we apply the limits we will get this as 1 plus e raised to minus I omega pi divided by here 1 minus omega square. This is the required Fourier transform of the given function. Now consider the unit step function u of t defined by u of t equal to 0 for t less than 0 and is equal to 1 for t greater than 0. This is the definition of unit step function, and the corresponding Fourier transform is f of here u of t is equal to integral from minus infinity to infinity e raised to minus I omega t into f of t. Here f of t means the unit step function u of t dt, which is equal to integral from here the function is defined as two ranges. The function is defined in two ranges. First is t less than 0 means minus infinity to 0 e raised to minus I omega t, in which case the function is defined as 0, plus the second one is integral from 0 to infinity e raised to minus I omega t into, in this case function is defined as 1 into 1 dt. That is equal to the first integral will become 0 on integration. This is e raised to minus I omega t divided by minus I omega between the limits 0 and infinity. When we apply the upper limit infinity, the numerator will become e raised to minus infinity, which will tends to 0. E raised to minus infinity tends to 0, minus when we apply the lower limit t equal to 0, we get this is 1 divided by minus I omega, that is equal to 1 by I omega. This is the Fourier transform of unit step function. Now consider this function u of t minus a into u of t minus a minus u of t minus b. We have to find the Fourier transform of this function. By the definition, this is equal to we can write this as 1 for a less than or equal to t less than or equal to b, and 0 for all other cases. Therefore, by the definition of Fourier transform, we have Fourier transform of u of t minus a minus u of t minus b is equal to integral from minus infinity to infinity u of t minus a minus u of t minus b into e raised to minus I omega t dt, which is equal to, we have to split this integral as integral from minus infinity to a. In this case, function is defined as 0, therefore 0 into e raised to minus I omega t dt plus integral from a to b. In this case, this function is defined as 1 into e raised to minus I omega t dt plus integral from b to infinity. B to infinity means function is defined as 0 into e raised to minus I omega t dt. First and third integrals are 0, and the middle one is on integration we get e raised to minus I omega t divided by minus I omega between the limits a and b. This is equal to e raised to, when t equal to b, here in the numerator it is e raised to minus I omega b minus, when t equal to a, we get e raised to minus I omega a all divided by minus I omega. That is e raised to minus I omega a minus e raised to minus I omega b all divided by I omega. This is the required Fourier transform of this function. Now consider the function u of t into e raised to minus a t, u of t into e raised to minus a t, that is e raised to minus a t multiplied by the unit step function. We want to find the Fourier transform of this function. We have u of t into e raised to minus a t is equal to e raised to minus a t for t greater than 0, and this is equal to 0 for t less than 0, because u of t equal to 1 for t greater than 0 and u of t equal to 0 for t less than 0. Therefore, this product is defined as this, and the Fourier transform of u of t into e raised to minus a t is equal to, by the definition, Fourier transform is integral from minus infinity to infinity u of t into e raised to minus a t into e raised to minus I omega t dt. Here we have to split this integral into two. One is from integral from minus infinity to 0. In this case, function is defined as 0, therefore 0 e raised to minus I omega t. This is the function which is defined as 0 in this interval t less than 0. Therefore, this integral minus infinity to 0, 0 into e raised to minus I omega t dt plus integral from 0 to infinity. In this case, 0 to infinity means t greater than 0. Function is defined as e raised to minus a t. E raised to minus a t into e raised to minus I omega t dt. First one will become 0. Therefore, this is equal to integral from 0 to infinity. Here we can write e raised to negative of t into a plus I omega. dt. On integration, we get e raised to minus of a plus I omega into t divided by minus of a plus I omega between the limits 0 and infinity. When we apply the upper limit infinity, this numerator will tends to 1, that is e raised to minus infinity tends to 0 minus, when t equal to 0, the numerator is 1 divided by minus of a plus I omega, that is equal to here minus 1 divided by minus of a plus I omega, that is 1 by a plus I omega. This is the required Fourier transform of this function u of t into e raised to minus at. Now let me conclude this session. In this session, we discussed the Fourier transform and some examples of Fourier transform. In the coming session, we will discuss some Fourier transforms of some elementary functions. Thank you for watching this session. Have a nice day.